The development of quantum mechanics can be separated into four parts. Development begins with Boltzmann's effort to quantize individual particles in an ideal gas. Max Planck used Boltzmann's statistical ideas to refine the understanding of radiation in the blackbody experiments. Einstein's photoelectric effect explanation incorporated aspects of Planck's theoretical development. The Niels Bohr excited state atomic model utilized the energy quantization proposition from Planck and the quantum of action proposition from Einstein. Wave equation theory formalized the Bohr model into three-dimensional form. We will go through the development. The starting point for Boltzmann's work was the ideal gas equation. It is an energy equation with pressure and volume on one side. Pressure is force per unit area, volume is cubic meters. Multiplication yields force times distance, which is the definition of work and therefore energy. On the other side of the equation are many molecules or atoms with an average kinetic energy represented by temperature. Realistically, some are moving faster while some are moving slower. Gas particles have a statistical distribution of kinetic energies based on the overall temperature. Boltzmann's constant, Kb, is based on the equipartition of energy. It is used to generate the Maxwell-Boltzmann distribution, which is a bell-shaped curve. The exponential factor modifies a primary relation. There's no way to verify the distribution because the velocity of each molecule in a volume cannot be measured individually and simultaneously. The blackbody experiments involved measuring the spectral intensity of a perfectly radiating metallic surface at thermal equilibrium. Several theorists attempted to solve the problem. Wilhelm Wien was almost successful. Planck, a contemporary of Boltzmann, produced the most accurate mathematical model. Planck modified the Boltzmann exponential relation slightly and went to great lengths to describe the energy of the radiation in the blackbody. There was no atomic description at the turn of the century when Planck and Wien did their work. We can examine the phenomenon using the Bohr model of the atom and Larmore's radiation formula. Using the damped-driven oscillator assumption for atoms in the metal vibrating against each other, we can see that the energy of the vibrating atom is proportional to the square of the frequency. The nucleus is in view here. Electrons do circulate at quadrillions of revolutions per second and would contribute to the total radiation picture, but the nuclear charge is the dominant feature. The four phases are separated into R1 through R4. 2 phases radiate and 2 don't. This is identical to the waveform generated in a dipole antenna. It is standard AP generation. Energy radiated by the moving particle oscillator is proportional to the frequency raised to the 4th power. This is from Larmore's formula. The Stefan-Boltzmann law states that radiance is proportional to the temperature raised to the 4th power. Both confirm Kirchhoff's assessment that radiation emanating from and absorbed by a blackbody operating at steady state is proportional to frequency. This was Planck's starting point for what would eventually become the Planck relation employed in his mathematical model. The Planck relation is a simple formula, epsilon equals hf. Epsilon represents a single atomic radiator. Frequency is the only variable. H is Planck's constant. Amplitude is not considered. Planck reconfigured Wien's basic mathematical model and proposed the statistical oscillator implied by the epsilon equals hf characterization. He separated the average oscillator out and effectively proposed an energy subset in the volume for each one. Here are the spectral energy density and spectral radiance formulas with the same frequency cubed relations and Planck's modified exponential shaping the curve. Mode density and average oscillator energy are parts of Planck's analysis of the phenomenon. Since an oscillator's energy is continuously reflected in the zero-loss blackbody, the modes were assigned a frequency commensurate with the boundary condition that there be a reflective node to return the radiation into the cavity. The standing wave idea was formalized, and the quantization of energy was implied, corresponding to a segregation of frequencies. Since a radiator, by definition, is quantized, the radiation it produces was also thought to be quantized.